Good morning, good day, everyone. As a part of our collaboration with the SPE Aberdeen section, we have a lecture today presented by Mikey van Mourik. He's a senior hydrogeologist at TownRock Energy, and he'll present to you today on the topic on geothermal energy, the heat beneath your feet. Just to briefly go over the agenda, we'll listen to the Mikey's presentation, and afterwards we'll go over to the Q&A session. If you're feeling more confident about putting your questions in the chat box, please do so. We'll just read them afterwards. If you're okay with asking question after the presentations, please do so. So Mikey, yeah, the floor is yours. We can see your presentation, so everything's fine.
Excellent. Thank you very much, and thank you for having me. Yeah, as you said, this is a presentation on geothermal energy, and I have an agenda that I'll come to in a few slides. But to begin with, I'll just give you a quick introduction on myself and TownRock Energy, the company that I work for. So I am a hydrogeologist by background, with 7 years of industry experience. And last year, I wanted to kind of change from the general hydrogeology industry into something that was tackling climate change, but still using that skill set. Um, I kind of started in the mining industry and then worked in the water resources industry for a while. So it was an exciting opportunity to join Townrock and start kind of being involved in geothermal energy, which, as I saw, kind of was a great way of offering an alternative to fossil fuels for heating and even electricity production. And since joining TownRock, I've worked on a number of mine water geothermal projects, as well as recently just completing a large-scale feasibility study for deep geothermal project in Scotland, which will be one of the case studies that I discuss in this presentation. TownRock Energy itself. So we were established in 2013 to commercialize geothermal heat in the UK primarily. Since then, we've started some projects abroad as well, but we kind of started focused on the UK. We're a team of 10 based in Edinburgh, in Scotland. And we're a consultancy and primarily a consultancy company, but we do deliver and operate geothermal systems as well. And over the last decade, we've built several first of the kind projects, and currently we're operating the only two privately funded mine water geothermal heating systems in the UK, which again is one of the case studies that I'll come to in this presentation. So just to give you an overview of what this lecture will be on. So I'm just going to begin. I'm not sure what people's background on geothermal knowledge is, so I'm going to start kind of with the basics and build up. So yeah, forgive me if it's stuff that you already know, but I thought it'd be easy to kind of as a segue into the rest of the slides. So I'll just give a quick introduction to that. Then I'll move on to the ways that geothermal can be used and the different technologies that can be used to kind of tap into that heat. I'll then talk about the case studies. I've got three case studies from TownRock Energy's projects, which I'll go through in a bit more detail. And then finally, I've kind of done a little bit of reading around the kind of geothermal potential in Ukraine as well. And this will hopefully lead into more of a kind of discussion between everybody. And I'll be really excited to hear your thoughts on this as well after this talk in the Q&A session. So to begin, what is geothermal energy? So I'm just going to move this a little panel so I can see everything. So you're harnessing natural heat from the earth, and this is natural heat that comes from the core of the earth, which is continually heating the earth's crust. Now, generally speaking, although it is very variable around the earth's surface, every kilometer you go down into the earth, you're increasing temperature by about 20 to 30 degrees, but 26 degrees is a kind of good estimate of that. As I come on to later, that is quite variable. And in Ukraine, there are some parts where it's only 20 degrees Celsius per kilometer, but other parts where it's a lot more than that. So 26 is generally considered the kind of average increase. When you tap into this heat, you can use that for various kind of things at surface level. So that can be renewable heating of domestic kind of homes or heat networks or kind of industry as well. Cooling, kind of on the flip side of that, can be used for. And if you have temperatures hot enough, about 150 degrees Celsius and higher, You can even get electricity production as well. Um, Around kind of the Earth, you have this background geothermal gradient, but generally speaking, granites offer a heightened level of heating due to naturally occurring radioactive decay. Um, and so I'll come on to this as well in one of our projects that we did in Scotland as well. So, kind of stripping that right back, why is the Earth hot in the first place? Well, there's still residual heat from when the Earth was first formed, and that is slowly radiating out from the Earth's core out to its surface. And so you're constantly getting that replenishment of heat. But as well as that, and this is where it's more prevalent in granites, you have continuous decay of radionuclides, which is primarily uranium, potassium, and thorium, and that generates heat as well. So those two things combined give give the Earth that heat that we can tap into. So when you have this heat, what ways can it be used? Generally, people think about places like Iceland and New Zealand and Italy when they think of geothermal heat because it is so close to surface and you actually have steam kind of coming out of the ground. However, if you're using it in other parts of the world where it's not so close to surface, you need to use boreholes. So you need to drill down to access that heat. And I've just got here some of the various technologies that you can use to harness that heat. So starting with the shallow geothermal, which would be your lower temperature stuff, and it's worth pointing out at this stage, you can use geothermal as shallow as 3 to 5 meters below ground because it's such a stable temperature. Although you're only dealing with maybe 10 to 15 degrees Celsius, that's enough kind of temperature to use if it goes through a heat pump to supply kind of reliable and continuous heat energy. So in your shallow systems, you would have ground source heat pumps, which are essentially flowing a refrigerant through either a kind of a horizontal system close to surface or in boreholes as well. And you can have what you have like a U-shaped pipe where you pass refrigerant down, it heats up as it goes down, and then you have that recycled back up and you extract the heat at surface. That's a closed system. It all happens within like pipework itself. Another shallow geothermal system, which I'll come on to, is the using of flooded mines, where you're actually pumping out water, cycling it through a heat pump again, and then pumping that water back in, so creating a sustainable loop whereby the water, by the time it's come back to your the place that you're taking it out from, has heated back up to that original temperature. There's one technology missing from this diagram, which is a very similar concept to that, but you're just using natural groundwater instead of mines. And I'll come on to that in the next slide too. Now, deep geothermal is often where the kind of excitement happens because you're dealing with much higher temperatures. So we have, first of all, we call hot sedimentary aquifers, where you're drilling down into kind of between 1 to 3 kilometers depth, so it can be higher, and you're using the natural groundwater that exists in that aquifer, pumping it out, using that heat, often directly. It doesn't have to go through a heat pump if you can get it to 60 degrees Celsius and over, because that's enough to supply heating. And then you're pumping it back down. And again, if you have two wells, one to extract, one to inject, then you are having that continuous source of kind of hot water coming out, using that heat and pumping cold water back down. Another method is using old oil wells that have been abandoned. There are various ways that you can recycle these wells. Generally, the simplest way is to put down a single pipe which has an insulated inner pipe, and like the ground source heat pump, you pump down a refrigerant or a fluid. It gets hot as it goes down, and you pump that back up the middle of the well. So there is opportunities to recycle old oil wells in this as well. And finally, and kind of often is the most exciting, is the really hot granites that you get at depth. And you can there's projects that have drilled down to 6,000 meters globally to access this heat. And you are typically again pumping down cold water, that heats up, and you're pumping out the hot water again. So again, you're creating this loop, which is generally how geothermal technologies work, creating this loop where you're kind of cycling water through or fluid through to extract that heat back up to surface. So just going to do a bit of a, I've kind of touch on some of these, but these are just some diagrams to show how each of these shallow geothermal systems work. So the closed loop system, as I mentioned, you usually have what's called a U pipe, and you have one borehole with a one pipe going down, one pipe coming up, and it's heated as it goes down and comes back up hotter. Open loop is a system where you're using the natural groundwater, so you're pumping out groundwater, putting it through a heat pump, and injecting colder groundwater back down after you've taken between 5 and 10 degrees Celsius out of that water. And what we do a lot of at TownRock is mine water because there's a lot of mines, old abandoned mines in the UK. And the idea is here is that they offer a fantastic um, kind of area that water is stored. So there's a huge storage potential of that water. You can take it out, use that heat, and pump it back in. And if you've got two mine seams that are connected, that water will find its way back to where you're taking it from, and you'll have a really good kind of loop that works. Deep geothermal, there's two methods of extracting heat from deep geothermal. So the first is conduction, where you have a closed system, similar to the closed loop one I just mentioned, and you're taking heat from the natural conduction of the rock into a fluid that's cycling through it. So the fluid doesn't have contact with the rock. There's a pipe in the way, and it's much more reliable system because that heat is continually coming through. You can do this anywhere in the world because you just rely on that natural geothermal gradient. However, it's not the most efficient system, so you don't get the same outputs as you do from the method I'll come on to after this. There are two main ways of doing this. It's a simple way, which is just one singular pipe that you use. This can be vertical or it can be inclined as well. Or there's what's called advanced geothermal systems, which use a much more intricate set of pipe work that increases the surface area. So you have more heat coming out of that rock that you're able to take the heat from before pumping it back up to ground. The one caveat of this system is it's incredibly expensive and there's a lot of technical drilling challenges as well. So this is very much in its infancy, whereas coaxial has been around for a long time and is much more easy to implement. And then finally, deep geothermal using convection. So as mentioned, hot sedimentary aquifers, where you're taking the natural water that exists from a good aquifer at depth, beyond 500 meters, but typically kind of 1,000 to 3,000, taking that water out, using it directly, and then pumping it back in. You need to have a good water connection here, though. You need to have a good aquifer, otherwise it won't work. So this technology is limited to kind of more specific areas. And then finally, in engineered geothermal systems is where you're drilling two wells down and creating those connections yourself. So by usually hydraulic or electrical stimulation, you're actually creating new connections in the ground. And that's, of all the technologies I've just presented, the most efficient because the surface area that the water has to go between the cold well that you're injecting down and the warm well that you're bringing water out, hot water out of, is a lot higher than the other technologies. And so if you can develop one of these systems, and I'll come on to this because there's quite a lot of examples of these globally, you can get on the order of kind of 20, 30 megawatts of heating output, and even higher temperatures can lead to electricity production as well. So just some case studies that TownRock have, which I'll talk about. The first is Lanchester Wines, and this is a wine warehouse in the north of England, and we're using mine water geothermal here. So there's a lot of extensive mine workings underneath this warehouse that we're using to supply heat to the warehouse and keep the wine in this warehouse warm through the winter months. So just as a map, so it's in the northeast of England in a place called Gateshead, and we have two systems here. We have one called Nest Road, which has 1.2 megawatts of capacity, and one called Abbotsford Road, which has double that. And these went operational in 2018. These are a private company owns these. TownRock operates them on behalf of this company, and they're the only two privately funded mine water systems in the UK right now. And I'm just going to give you a bit of an overview of how these work to kind of, if you remember the diagram of the mine water, this is kind of a more detailed version of that specific for this site. So at this Abbotsford Road, we're taking water out in that red well from about 265 meters and it's 19 degrees Celsius. That then gets pumped to surface we extract 8 degrees Celsius from that water before it gets pumped back down into the mines. As you can see, there are two separate mine seams here that are connected, and that allows for a good supply of water, but without causing what we call thermal breakthrough. Whereas if you had what's my point? If you had two wells, one extracting and one injecting close to each other, they would start interfering with each other, and you wouldn't get the same amount of temperature coming out of the well. So it's important to have them separate, separate enough so that you don't get the thermal feedback, but still allow slow percolation of water so that you still get that cycling of water throughout. In Nest Road, where it's kind of a mirror image of Abbotsford Road because we're taking water out of the more shallow seam, so it's not as warm. We're taking 4 degrees Celsius out and then we're injecting into the deeper well. And because these systems are about 600 meters apart, because they're the mirror of each other, they actually complement each other quite well. You're not taking out too much heat and you're not injecting too cold water. It's kind of a nice balanced system as a result. And once we bring this water surface, we put this temperature water through a heat plate exchanger, which allows that water to heat an internal fluid. That fluid then goes through a heat pump and gets risen to, I think it's 50 degrees Celsius, and that's enough for the space heating to keep the warehouse warm. And just to give you an idea of what this looks like inside the plant room, so on the left you have the plate heat exchanger, which has 60 very thin plates, allows the mine water to warm the internal water before that water then goes through these two heat pumps here. And that heat pump raises the temperature from 19 degrees up to 50 degrees. There are always some issues with mine water systems. One of which is water chemistry, and as you can see, the water that we're using was very rich in iron, and as that iron oxidized, it actually caused this iron ochre buildup on the plate heat exchanger you can see here, in the pipework, and on the impeller pumps as well. We've since rectified that by slightly altering the system and preventing oxygen from getting into it. But yeah, these are some of the challenges that we've had to face as operating this system. Next, I'll move on to body heat. And I should say, if you want to ask questions about any of these sites afterwards, please feel free to kind of write them down and ask them. So this is now moving to a project of ours called Body Heat, which is in Glasgow. So that's on the west coast of Scotland. And this was actually an event space. It's used as a music venue and kind of a nightclub as well. And we had a client that had a really strong net zero vision. They wanted to have renewable heating instead of using their gas boilers. And so we developed a system where we would kind of use heating and cooling using the closed loop system that I showed before, where you have those pipe works that go straight into the ground and you have that U shape going back up to provide cooling to the event space when everyone was dancing and getting warm instead of using air conditioning, and then capturing that heat and pumping it back down into the ground for use later, almost like a battery. And so this is a diagram of the system. So as everyone dances, they get hot, we capture that heat, we transfer it into the ground, and then that heat is stored for later use by other users for heating, or in the winter months if that event space needs to heat up instead of cool down. And the idea was not to let people's heat escape the atmosphere and get lost forever, but to keep it and store it on the ground for use later and create that battery system. Just give you a bit of an overview of how the system itself works. So we have 12 boreholes, each with that U-shape configuration. They're spaced 8 meters apart so that they don't interfere with each other. If they were too close, they would start kind of stealing each other's heat from one another. So it was important to keep them 8 meters apart, and that was a modeled distance we deemed appropriate. And so far, it's working, and that's been operational as of 2022. You can see here the 12 boreholes spaced in what's a garden now. So it's actually, you can't really see the boreholes, they're very well hidden. And that's one of the advantages of geothermal, is that the footprint is very low, and you can, unlike other renewables such as solar and wind, which you can see from a long way away, geothermal is very much hidden from sight. And this is just giving you an idea of using the drilling rig to install these systems. So you can see this pipe work here, which is this U-shaped pipe work. It gets put into the ground and then connected up to a kind of larger pipe system and then eventually to a heat pump. to increase their temperature from about 10 degrees up to, again, about 50 degrees when you're heating, and then the same when you're cooling down and capturing that heat and putting it. Finally, the third case study is one that we finished recently. So I've tried to give you a bit of a mixture of different technologies. So we started with mine water, we then had closed loop, and this was a feasibility study. So nothing that's been created yet, but we were investigating the use of deep geothermal in Aberdeen in Scotland. And it was to replace these gas boilers. It was for a hospital client that we've been working. They currently run their entire heating system on gas boilers, and they want to look to replace those with a renewable source. So that's why we're investigating geothermal. So to do that, we had to model what was possible to get from the granite underneath the hospital itself. So we needed to look at two things: the heat demand of the hospital, what were the temperatures that we needed to target, what was the peak demand of that heat, and what was the base load, what was always required. In conjunction, we also have to look at the geology. What are the properties of the granite? How deep does the granite extend? How hot is it? And are there any natural fractures that we can tap into, or do we have to create new ones? And so this is just to give you a kind of an overall map of the granite that we map. So you can see Aberdeen in the top, right in the northeast of Scotland here. The hospital site is based in the middle of this granite here, this pink outcrop, and we did some geology mapping to model how extensive that would be on the ground based on some literature as well, which did some gravity surveys in the past. And we predicted it to be about 7 to 8 kilometers depth, which is plenty for a system that we wanted to design, which was going to be to between 3 and 5 kilometers depth. And so we modeled this could be a successful project, and it would require drilling down 3 wells, one to take the water out, and two to put water back in, and have connections between all 3 of those wells, so that you're cycling this water between the wells and taking it back out once it's heated up. And we modeled that you could kind of get up to about 120 degrees Celsius. So not enough to create electricity at these depths. You'd have to go deeper for that, but plenty to generate a lot of heating for the hospital. And this is just to kind of give you some other examples of deep geothermals that are in operation. So there was a project in Finland. Actually, it's not in operation currently, but they have successfully managed to drill down to 6 kilometers depth and create connections between the wells. And so a lot of learnings have come from that project. And then in the UK, there's a project in Cornwall in the south of England, which is supposedly going live this year, and they have drilled to 5,000 meters with two balls, and it's actually hot enough to create electricity there. So they have an electricity plant joined to that. So it's very exciting for the geothermal industry when that goes live later this year. So finally, just going to now discuss the geothermal potential in general, but kind of I've got a few maps that focus on Ukraine, and this is where I'd like your engagement as well after the talk in the Q&A session to see, if you have thoughts on this too. Firstly, just beginning with how the carbon footprint of geothermal compares with fossil fuels such as coal, gas, and oil, but also other renewables as well. So there's a bit more of a range for geothermal because it depends on the depth that you're drilling to, how many boreholes you need, and the kind of materials that are going into it. But generally speaking, once you have implemented a system, the operational CO2 outputs are really low here. So it's a really good way of getting that renewable heating. And then some of the risks that come with this. So I think it's always important to talk about the risks and kind of how you would go through a project from beginning to end. Some of the main risks that we identified in the project that we did in Aberdeen were geological, first of all. Have you got the aquifer you want to aim for? Have you got the granite you want to aim for? And is that going to be sufficient enough to supply the heat that you need for a geothermal system? The technical challenges are the drilling challenges that you need to navigate. We recently had a project in Aberdeen where we were drilling into mine workings, and we hit mine workings that we thought were not there, and it actually created quite an issue because they were before the natural groundwater level, so they were dry, and we wanted to target those that were deeper, but it was really challenging to get beyond the unwanted mine workings. And then the technical challenge is if you're drilling deep, does it get too hot to drill? They're having this issue in the US a lot at the moment. There's a project called Fervo, where they've done lots of really exciting work and lots of this engineered geothermal systems. But there are times when the heat is actually so much that drilling has to stop for a while, or they need to design really robust drilling equipment to deal with the kind of 300 degrees Celsius that you could be dealing with. One of the main ones is the financial risk as well. There's no secret that geothermal is very expensive upfront. It has a large upfront cost. The advantages come after long periods of time, because if you have a 40-year project, the operational costs are so low that it does pay for itself after a while. But because there's such large upfront costs, that does carry a financial risk if your system isn't as efficient as you modeled it to be. And then finally, social and environmental risk as well. Do the people living in that area want something like this? People often get scared of things being drilled underneath their feet because of size, like microseismicity, or noise pollution, light pollution. Do people understand what this project entails? And so that's something that always needs to be kind of taken on board when you're doing a project like this. And the environmental risk as well. Have you covered all the requirements from the environmental perspective to make sure that you're not going to have a negative effect? And here I've just got a graph that shows in this black line how your project risk or project uncertainty reduces as you go through a project. So generally, TownRock have a model where we would do a scope study first to just see if geothermal is possible in an area. We would then do a discover phase where we do a feasibility study to see, how successful a project might be, what the design might look like, and kind of what outputs you might get from that. We would then do a prove phase where you're drilling an exploration bore to test what is actually physically underground. And this is where your project risk really comes down. It requires a bit of upfront cost because drilling is not cheap, but your uncertainty really does come down. And as you go and move into actually delivering the project and then operating it for kind of 30, 40, 50 years, your uncertainty reduces year on year on year. So at the beginning, it can be quite high, but at various stages, it just low as you go through. Now, finally, I just did a bit of digging and found some maps that kind of highlight the geothermal resource in Ukraine. And there was two main kind of areas that I noticed: the Precarpathian Basin here, put in the kind of purple, and the Transcarpathian Basin. And both of these are either really promising or highly promising. And this is looking at the geothermal gradient that exists in these places. So this is more looking at the deep geothermal options, such as the engineered geothermal systems and the hot sediment aquifers. So I haven't gone much more in detail than that. It'd be great to know, if people in this call know much about the geology of these areas and what they look like. And I don't know if people have known any studies that have happened in these areas so far. But estimates have been that you can replace, a large amount of gas and oil with geothermal energy, and it can be a key player in reducing the reliance on traditional energy sources. Because as well as being low carbon, one of the advantages of geothermal is that it's incredibly stable. You have 24/7 power as opposed to other energy sources or renewables where you have to rely on wind and you have to rely on the sun. Because you're constantly getting that heat from the earth, it's available 24/7. So it offers a really stable baseload source of energy, whether that's heating or electricity. Um, and it's not volatile based on the prices of gas, etc. And then finally, just thinking about mine water geothermal, I just had a bit of a look at where the coal deposits were in Ukraine and where existing mines might be abandoned or operational, where you might have potential to tap into mine workings that are flooded and use them for mine water geothermal. So again, it'd be interesting to hear your thoughts on these as well. And that's it from me. Thank you for listening. And yeah, happy to answer any questions and have a discussion on geothermal in general, whether that's on specific technologies or just as a concept overall. Thank you very much.
Yeah, thank you very much, Michael, for this interesting and very beautiful presentation. We have a few questions in the chat box, but
Okay.
if anyone would like to ask directly, so please feel free, and then we'll jump over to the questions in the chat box.
Hello, Michael. Thank you very
Hi.
good thank you very much indeed for the brilliant presentation. And I'm surprised that you managed to get in so deeply to Ukraine. Huh? I am here phoning from Oslo, and I have been in Ukraine the last 7 years, so I know the potential and the possibility we have there. And also, I was working with Hydrogeologist University. But what was very interesting is that this geothermal is also related to the, uranium storage, because the biggest problem is usually the cracking of the rocks. And using geothermal potential is very important. So that is one extension. And that is also potential because we have, of course, in Ukraine and very many European countries, this problem of storage of uranium. In
Hmm.
addition to that, I was working in the North Sea when we were using cold water and using a hot reservoir to crack the rock. So that was also some kind of the experience. And of course, my interest is in multi-fractured horizontal wells. And then you show the case with multi-fractured horizontal well, and where you are injecting probably water, and then in the same time you're getting heat out through the same.
Mhm.
So I put in the chat some kind of the interest for what kind of the software you recommend for such event and also for the injection and so on. That I will appreciate having your answer. Thank you very much, Branimir.
Yeah. Okay. Did you say the software or?
Yeah, the software, yes.
Yeah, okay. So, in terms of so far in our Aberdeen project, we've done modeling to kind of suggest how what the thermal reservoir is, and that was using a reservoir software modeling program called CMG Stars, which can give you an idea of, if you were to model each of these fractures. I can't remember exactly how many we modeled for this particular design. But you can use that to estimate the output from a certain depth if you input things like temperature and water flow, etc. Um, the software for the actual stimulation itself and the actual kind of modeling of how that would operate, I can't comment on because I haven't been involved in a project yet that has done this. I know I'm trying to rack my brains. In the US, in Fervo, they're doing a lot of stimulation at the moment, and I think they're using a program. It was called ResFrac, which is how you're actually mapping and simulating how the fractures will propagate and how they are created. Um, and so, yeah, I think if we were to get to a project level where we're doing that, I think that's the kind of software we would use. But I think you make a really good point about the thermal stimulation as well, where you're using hot and cold injection of water to put pressure on the rock that will then break it up. As another technique, as well as the hydraulic technique, where you're using pressure, water pressure, to make those fractures, which yeah, I'm sure you know about as well. But yeah, I think so. They're the kind of main technologies for actually creating the fractures. But then the simulation software, I can't comment on what we would use because we haven't done it yet. But I know they're using ResFrac in places like Fermo in the US.
We at Poltava University, we are trying to follow that, and based on that, we have CMG software, we have
Okay.
RFD T Navigator, and as well we have
Yeah.
Eclipse. In
Uh,
addition, we have another software which is Seagull, coupled with Petrel, and that is the latest technology, and that is something very, very new. It's coming
right. Okay.
last year. So
Okay.
that is what we are following, but we are not still in. We have now connection free with Croatian's team, And the university, I'm even having a data on one geothermal field, and I'm contacting some of the best geologists in Ukraine for that. And then
Right.
also I am here investigating other opportunity in Norway. So that is
Yeah. Okay.
for you. Well, we try
Great.
to
That's a,
emulate. We are not so well as you are, guys, but I appreciate your presentation, and of course, it's very welcoming that we support Ukraine fully as we can. Thank you very much.
yeah. No, thank you. And yeah, and it sounds like you know more than I do on the simulation side of things. So I mean, if you want to get in touch and let me know about some of these projects and softwares that you're using, I'd love to hear more because that all sounds really interesting.
Okay, thank you.
Okay, I guess we'll move on to the other questions. So we have actually two questions from Roman. First one, in case of use of hot aquifer as heat source, how do you estimate the presence and volume of the aquifer that could be extracted, especially in case where wells are not present?
Yeah, I'll tackle that one first. That's a really good question. There are various ways that you can make those estimates. But you're right. If there are no wells present, the uncertainty is higher. If you have nearby wells, then and they have data on the temperatures at depth and also the volume of water that was extracted during drilling, for example, then that is so helpful for making your predictions on designing a system. In places where we've done that in the UK, often there are oil and gas wells to that depth because you're dealing on deeper kind of systems of 1 to 3,000 meters. You wouldn't typically have water wells drilled that depth, so you're really relying on oil and gas. So that can be really useful. If you don't have that data, then there are other ways of modeling that with granted increased uncertainty. But that would come from being able to map where that geology will lie underground. If you can map kind of from the surface, but if you know the angle of that's going into the earth, and then often kind of extensive geological studies in various countries, and you can actually get the depth that your aquifer exists, as well as the thickness of your aquifer, then you can start making predictions on the temperature based on that depth. And yeah, the volume is something that is uncertain and really does require the exploration wells to fully prove what exists there. Because if you know, well, first of all, you might have data from that same geology in a shallower area, which may have water wells, and so you can kind of build a picture from using data from all over the place that is the same geology or the same unit. But you have to bear in mind that as you go deeper, the pressure of the rock above actually reduces the size of the pore spaces that water exists in, as well as the fractures. So it's actually probably going to be lower than it would be at a shallower area. So all these things considered would build into your model that then you would assess whether it's a viable system or if there's too much risk. I hope that
Oh,
answers that
okay, I
question.
understood that. Thank you very much for the answer. And the other question from Rowan is, in case of geothermal heating, not electricity production, how do you quantify the amount of energy that would be produced per well? In other words, quantitatively, how geothermal would be cheaper or more efficient than using conventional heating methods?
Hmm. Again, that's a really, really good question. So there are again various ways of doing that, and it depends on the technology that you're using. So if we start with shallow geothermal, um, you it depends on whether you're using a closed system, so whether you're just drawing heat from the rock into like a passing fluid within pipes, or you're using an open system where you're taking water out directly, and you can use the flow rate of water that you're taking out as well as the heat that you're extracting to determine the quantity of heat that you can get from each well. So there are various kind of methodologies that go into that, but kind of at its basic level, your flow rate times the what's called a delta T. So it's the difference between the temperature of the water you're taking out versus the temperature of the water you're putting back in. So let's say that's 10 degrees, and the flow rate that you're passing it through at would give you a general idea of the total heat energy that you're taking out. And then you can use that data and model based on drilling cost estimates for building a plant, all the pipe work that's involved. Is your system viable financially? And you can model a what's called a levelized cost of heat, where you're getting an actual pence per kilowatt hour price for that specific geothermal system, and then you can compare that versus gas, versus air source heat pumps, biomass, all the other kind of heating technologies, and you can get a level playing field to compare them and see whether in that area with those flow rates, with those temperatures, is geothermal a good option? Because in some places it won't be, and it'll be too expensive. So you need to, yeah, all this will feed into the model on whether it's worthwhile doing in that area or not.
Okay, thank you. And we have another one. It's also related to the viability and the infrastructure as well. So it's a question from Mikola. For old oil wells to be viable for geothermal energy and hot water extraction, should they be situated very close to end users of the energy? Are there any real-world examples of old oil wells being used for geothermal energy? If so, what is the ideal distance these wells should be located from the consumer to be economically viable?
Yeah, you're asking really good questions and testing me as well. So I think this is one of the caveats with using oil wells, essentially, because especially in the UK, most of our oil and gas wells are offshore. They're in the North Sea, off the northeast of England and Scotland. And so you're exactly right. If you're not producing electricity, which is more transportable, but you're producing heat, your efficiency really reduces if your distance to the end user is high. So yeah, I would say for repurposing oil and gas wells, it probably has to be onshore wells for it to be viable, unless you're supplying heating directly to like an oil rig offshore, for example. I don't know if that's been done anywhere. But yeah, I think the distance is really important, and you want it to be as low as possible. You can use like kind of thermal insulated piping to make that system more efficient, but I would say you wouldn't want to go more than kind of a kilometer before it starts becoming incredibly expensive, and probably even less to make it economically viable. Because the longer pipe work you're needing, the less kind of beneficial your system is going to be. And that's one of the caveats with heating in general, is that your production has to be really close to your end user. And so you could find the most amazing geothermal resource, but if there's no one around to use it, and you need to pipe it kilometers and kilometers to use it somewhere, then it might not be viable because it's too expensive and it's not as efficient enough because you lose that heat as it's being piped. In terms of real world examples, there have been a lot of test examples using, as I mentioned before, the kind of simple coaxial system where you're you're using one pipe that goes down a vertical well or can be inclined with an internal insulated pipe and passing fluid down the outside of the well and back up the middle of the well. I don't know if it's been really proven whether that's financially viable on a large scale. But it's one of those things that if the one advantage of repurposing oil and gas wells is that you don't have the drilling costs, which are a huge part of the geothermal delivery. So yeah, I think it would have to be on a case by case basis. I haven't seen one that I've been kind of that I can tell, yeah, that's absolutely kind of economically viable to go with. But I think, yeah, it's like other parts of geothermal, it's an area of research that's kind of always continuing. So, yeah, it'll be interesting to see if oil and gas wells and oil companies can repurpose these to deliver this energy.
Yeah, I guess we're coming very logically to another question from Yuri. So his question is, in case of having unproductive well, could it be repurposed for geothermal for heating purpose? And what steps and materials are required? For example, the tubing type and materials, any downhole heat exchanger?
Yeah. So presumably, do you mean an unproductive oil and gas well, or an unproductive geothermal well?
Yeah, I guess. I mean, he's here, but I guess it was meant the unproductive oil and gas well. Yeah.
Yeah,
Mhm.
because both can actually be true. But yeah, let's start with oil and gas. So yes, I think that is certainly the case. Especially if you were to drill an oil and gas well and found hot water instead of oil or gas, then and you had a good supply of water, then absolutely you could repurpose that geothermal that oil and gas well for geothermal. If you drilled a well and there wasn't much of a resource at all, there wasn't water either, then you would have to do just the system that I just mentioned, the coaxial system. And it can be a really good backup option. It kind of is a risk reducer because it's not, let's say if you're doing a geothermal project and you wanted to tap into a large water resource and you didn't find it, then this system would be a good backup because it can be done anywhere because you're just drawing heat from the rock. You don't need fluid, you don't need external fluid. It's just a less efficient system. But yeah, one of the projects that we've just kind of done and recommended on, that was our backup option. If your initial kind of high flow option doesn't work, this is a backup. And in terms of what materials you would need, um, I guess it depends on the depth and type of tubing you would need. But if it's, oil and gas wells are generally pretty deep. So, yeah, you would need that kind of insulated, insulated pipe work going up so the water can come up the middle, and a kind of a conductive casing so that heat can get from the rock through the casing into the fluid that you're passing down. I've not heard of downhole heat exchangers being used. I think generally you'd have your heat exchanger at surface, and then you would take that heat out, and then I think really with a coaxial system you'd be looking at needing a heat pump as well. I don't think you would get unless you do it really deep to like 7,000 meters. I don't think you're going to get, or you had a really high geothermal gradient. I don't think you're going to get the temperatures for direct heating, just because it's not as efficient a system. But with a heat pump, you can boost that up to 70, 80 degrees Celsius.
Okay, thank you very much. And I guess that's it from the chat box. In case someone still has some questions, so please feel free to ask them.
I mean, if there's a lot of people might be thinking of questions, I guess my kind of question to the group would be kind of based on what I presented in your previous knowledge as well as those maps I showed. What do people in this group think could be the potential of geothermal in Ukraine and how it can best be utilized? Maybe this is something people can go and have a think. I'm not expecting a full answer immediately, but that'd be my kind of main question at the end of this is, yeah, that what technologies would be most applicable to various locations in Ukraine?
Yeah, Michael, I'm not an expert in geothermal. I'm more into oil and gas, but I know there are a few people who are really doing some projects on geothermal in Ukraine. And what I know for just the basic that this map you showed, it's really true. I know that some of the companies, they're really thinking about it and pursuing the geothermal energy, especially on the Carpathian region, the pre-Carpathian and region that you showed. And I know that from what I know, they're reviewing the viability of these projects definitely. So yeah, if
Right. Okay.
anyone here could comment on that, that would be great.
Hi, Michael.
Yeah. Yeah, interesting to hear where they go the streets.
Hi, Michael. Sorry, I'm outside, so there might be some noise. But yeah, basically what Oleg said is true. We do have on the map that you showed, we have basically three regions, the one on the east and the two on the west. The one that you called Transcarpathian, which was like in red,
Mhm.
highly potential, you called it. Yeah, so that one, it has shallower geothermal potential because the heat source is shallower, and that's
Mhm.
where we have the subduction zone. So
Right.
yeah, that's more potential for what you call the shallow geothermal. What we have on the the pre-Carpathian Basin or Carpathian 4 deep. This one is looking more of deeper geothermal at around 2, 3, 4 kilometers depth. But again, depending on geology and where you are. But it has high potential in terms of repurposing, and we have some people living there. So it's also, that's a question. It's something I'm working on as my part of the PhD. And on the east side, that's also a heavily drilled area, which is a DDD, Dnipro-Donetsk Basin. That one also has a potential of repurposing oil and gas wells. But again, now that's a question of where it is, because the highest potential that you have is currently on the no-go zone.
Right. Okay. I might get that. I might get that map up actually. Can you still see my screen, or is it stop sharing?
Yeah, we can still see the screen, but it's the last slide. Yeah.
Oh, is it? Okay. Hang on, let's go back to that map. So, so do you mean these areas are?
Yep, correct. Yeah, but I think the question, and I think some people on the call might have more information than I do in terms of Transcarpathian, because I'm working on the pre-Carpathian Basin mostly. Well, not mostly, but completely. But Transcarpathian, the question is, even though it is shallow, the question is about the microseismicity and the safety and the risk of this project. But yeah, the heat source is there, and it's very close, so it's a sweet spot for the question for risk, and the cultural and the national acceptance of the geothermal put there. Considering the risk of microseismicity being there.
Do you know the general the depths and the type of technology that's being proposed?
No, for Transcarpathian, I don't know that. Maybe somebody else knows. But for pre-Carpathian, that's mostly drilling of 2, 3, 4 kilometers or repurposing oil and gas wells. But for Transcarpathian, I don't know.
Yeah. Okay. That's really interesting. But yeah, and I guess another question is, where you have areas of high potential, what are the potential heat or even electricity off-takers? Are there large urban environments around there? Are there kind of large industry that could utilize that heat? And as the question alluded to before, if you can have both together, then that's really when the potential is really high. So I don't know if that has been fed into this key, whether that is also looking at the potential in terms of if it's just the geology potential, or if it's also considering the kind of areas of urban population as well. I would think it's probably just the geology based on the type of map. But yeah, that's also something that kind of important to consider as well if you ever plan a project.
Yeah, I guess you're totally right. This one is only mostly based on geology, not on the population or whatsoever.
I think so. Yeah. Yeah, no, really interesting to hear that there's things like that in the pipeline. I think is that it? Questions?
Is this picture, Branimir again from Poltava University, is based on geothermal gradient, and is it any perception for how long it will not change if it is constant? And based on this constant, we have a constant map. But the question is that map can be long time present or not?
In terms of the geothermal gradient changing?
Yeah.
Yeah, I mean, not on human timescales, no. The geothermal gradient will be on geologic timescales. So yes, it would change as plate tectonics change and kind of increase, areas of volcanism, etc. change. But that would be on the scale of millions of years, and not on the scale of kind of human lifetimes or kind of human civilization. So I think that it could be a really assumed a kind of a very stable constant. The one thing that can change, and this is what we see in Scotland a lot, is that the previous ice ages actually cooled the ground, and so if you can, what's estimated is that the top 2 kilometers of ground in Scotland have actually a reduced geothermal gradient. And if you can get below that, you suddenly get a big increase because you no longer have ground that was affected by the ice ages. And that will be a similar factor in any place that was had glaciation over the last 2 million years. And so that can create kind of localized changes, but even then they're still very stable. They change over really long time scales of hundreds of thousands to millions of years. So no, the map itself will be it can be, assuming the map has used good data and is accurate, then it won't change in our lifetimes.
Michael, actually, following Branimir's question, that's a good question that he asked. In terms of geothermal potential, we agree that it will not change because the presence of lithospheric thinning and the subduction zones, that doesn't change that fast. But the question is the aquifer presence. So if we're using aquifer, the hot source, the aquifer or the hot water, how much time would it take? Can we deplete the hot aquifer, and how much time would it take to recharge? So that's a question.
No, that's a really good point. I think that is absolutely something you need to consider when doing a project such as this. And you see this globally just through water use from water wells and areas where overpumping of aquifers has led to water level decreases and in some places complete drying up of aquifers. So yes, it is definitely the sustainability of that system definitely needs to be assessed. Generally speaking, because of the depths that you're dealing with for hotter water, you don't compete with normal groundwater use for drinking and irrigation because the depths are very different. So that increases you're not kind of hampering existing water usage. But if you were going down to 2, 3, 4 kilometers, then you absolutely need to model how long and how sustainable that system is. And you can do tests with wells that exist. So you have to drill first. You can do tests to assess how long that system will be sustainable for and how, if you're likely to have a reduction in flow rate over the years, then that's something you'll completely need to consider on a project by project basis. But that factor is something that could be changeable. If you get into a good aquifer, they're going to have a huge resource of water. So when you're planning where to target, then that's also a key component of that is how good is that aquifer predicted to be. And if you get a good one, then you can pump for. I mean, there's some water wells that have been pumping for hundreds of years and still getting the same flow rates as they were hundreds of years ago. So, and in the UK, we have some really, really productive aquifers that just continually get pumped and pumped by water companies, and they continue to do well. And you just monitor how, if they are starting to go down over the years, and if they are, then you need to reduce your flow rates.
Okay, I guess that's all for
Yeah.
questions.
Okay.
Yeah, again, Michael, thank you very much for the presentation. Very interesting, and for the very good discussion we had with the people here and with
Yeah. No, thanks very much for having me. And yeah, really interesting to hear all the questions as well and have that discussion. So thanks so much for having me. And yeah, all the best. I hope it was useful.
Yeah, very useful. Thank you.
All right. Thank you very much. Thank you, Alex.
Thank you very much. Yeah, goodbye.
Bye, everyone. Cheers.
Thank you, and thank you to you for organizing